Okay, so imagine you're trying to compare two really complex things. Let's say, I don't know, two different financial investments.
Hmm.
And you have a dozen different metrics. You've got profit margin, growth rate, transaction frequency, all these things.
Right, and they're all tangled up with each other.
Exactly, they're correlated. So how do you actually measure the true distance or similarity between them?
That is the fundamental problem. Your standard, ruler-style distance just falls apart when variables are related like that.
And that's where this idea comes from.
It is. This was the challenge PC Mahalanobis faced back in, I believe, 1936. He was actually trying to classify ancient skulls based on their measurements.
Skulls. Wow. Okay, so what did he come up with?
He developed what we now call the Mahalanobis distance. And the easiest way to think about it is it's basically the high-dimensional version of a simple z-score.
Ah, okay. So a z-score just tells you how many standard deviations away from the average a single point is?
Precisely. This does the same thing, but for a point in a space with many, many dimensions. And, this is the crucial part, it accounts for the overall shape and correlation of all the data.
So it's not just assuming the data points form a nice, neat circle?
No, not at all. That's the simplistic view. Real-world data, when variables are correlated, looks more like a distorted football, an ellipsoid.
An ellipsoid, I like that. So the shape of the data cloud itself matters.
It matters immensely. The Mahalanobis distance uses the covariance matrix to understand that exact shape. So a certain distance along the long, stretched-out axis of the football is less significant.
Then the same distance along the short, tight axis.
You got it. It's about direction, not just raw distance. It effectively performs what's called a whitening transformation.
Which sort of stretches that football shape back into a sphere to normalize it.
Yes, exactly. And because of that, the measure becomes unitless and scale invariant. You can compare apples and oranges, or in this case, dollars and kilograms, without any bias.
You know, that elegance in finding subtle patterns and anomalies, it actually reminds me of our sponsor.
Oh, yeah?
Yeah, this deep dive is brought to you by Silk. If your business needs serious help with AI training, automation, or even custom software development, they're the ones to call. They specialize in finding out where AI agents can make the biggest impact for a business.
That's a perfect fit for this topic.
It really is, so check them out for any of your AI needs at embersilk.com.
So back to that ellipsoid. The real power here, one of the biggest applications, is detecting what we call multivariate outliers.
Okay, so what does that mean in practice?
It means you can have a data point that on its own doesn't look weird in any single category. Its profit isn't too high, its growth isn't too low.
But the combination of all its values is strange.
The combination is what flags it. It's sitting way outside that typical football shape of the data, even if it's not extreme on any one axis.
I can immediately see that being huge for things like fraud detection.
It's incredible for it. Or quality control. It's used in cluster analysis, classification, even in finance. They use it to calculate something called a turbulence index.
A turbulence index? To measure what?
To measure abnormal behavior in financial markets. How far from normal the market is on a given day based on many correlated factors.
That's fascinating. But there has to be a catch, right? What if the data you start with is already skewed by outliers?
That's a great question. And you're right, the calculation could be misleading. If your average is pulled off center by a few weird points, your distances will be wrong.
So how do you fix that?
Well, there are more robust methods. Statisticians use techniques like the minimum covariance determinant MCD for sure to find a much cleaner, more reliable center and shape for the data first before calculating the distances.
So you find the truest normal before you start measuring what's abnormal.
That's the goal.
It really feels like the core idea here is that this measure transforms this high-dimensional correlated chaos into a simple standardized number, a measure of probability, really.
It is. And that kind of foundational thinking is what's driving so much of the progress we're seeing in AI and machine learning today.
How so?
Because by getting better at defining and modeling these complex systems, we're moving past just guesswork. We're building more intelligent and, frankly, more resilient systems for the future.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.